Good afternoon, everyone. My name is Dave Dagoon, and today I will be presenting my thesis titled Analyzing the Viability of Using Wave Energy Converters for Seawater Electrolysis. First, I would like to start off by acknowledging my thesis advisor, Professor Martin, for his continued guidance and support throughout this thesis. And I'd also like to thank Dean Werner, my reader, and Professor Harris, my editor, for their help on the written portion of this thesis. I would also like to thank the WebMech team for their help with developing the system, as well as the cost analysis. I'll begin by clearly stating my objectives, then going over some background and theory, then my design methodology, the cost analysis, finally my results and conclusions, and then I'll finish up with my recommendations for future work. So the first objective of this thesis is to develop a concept design for a wave-powered offshore hydrogen production system. Then the second objective is to perform a life cycle cost analysis on this system. So first we'll discuss what is wave energy. It is a renewable energy source like solar and wind, and wave energy converters can harness the mechanical energy of ocean waves to generate electricity. Wave energy is an abundant renewable energy source as the world's oceans have a global theoretical potential to generate up to 32,000 terawatt hours of electricity per year. In US coastal waters, this number is 2,640 terawatt hours of electricity per year. If the US coastal wave energy resource were to be fully exploited, it could power up to 60% of US annual energy demands. The wave energy density is defined in this equation, where rho is the density of seawater, g is the acceleration due to gravity, and zeta A is the wave amplitude. Wave energy transport is defined in this equation, where cg is the group velocity, or in other words, the speed at which wave energy propagates through a wave. This value is used to evaluate a location's wave climate and is typically expressed in units of kilowatts over meters of crest width. So wave energy, the two wave energy converter types analyzed in this thesis are oscillating body systems and overtopping devices. Oscillating body systems consist of a moving body secured to a fixed point. As this moving body encounters waves, it exhibits a relative motion to the fixed point, and this relative motion is used to drive a power takeoff device. The two types of oscillating bodies of concern in this thesis are point absorbers, as seen on the top right, and surface attenuators, as seen on the bottom right. Next is overtopping devices. Overtopping devices accumulate water in a reservoir above sea level. This water flows out from the reservoir back into the surrounding ocean through a turbine outlet. This turbine outlet drives a power takeoff device. Now I'll answer the question, why hydrogen? The main problem with renewable energy sources is that they are intermittent and are typically most abundant far from large population centers. Hydrogen can offset the intermittency and inaccessibility of renewable energy by storing it for future use. Hydrogen is effective at doing this because it has the highest energy density of all known substances at 120 kilojoules per gram. When used in a fuel cell, hydrogen can generate electrical energy with zero greenhouse gas emissions, with the only byproducts of using hydrogen in a fuel cell being water vapor and heat. So electrolysis is a method for producing hydrogen. It is the process of splitting liquid water into gaseous hydrogen and oxygen. It is a carbon neutral process when it is powered by renewable energy. However, only 4% of global hydrogen production is through electrolysis. The remaining hydrogen is produced through fossil fuel-based methods such as steam methane reforming and coal gasification. These methods, because they use fossil fuels, contribute to greenhouse gas emissions. For hydrogen to meaningfully contribute to decarbonization, it must be produced using renewable energy sources. So electrolysis can be summed up through this equation, and it requires DC electricity input to split the liquid water into hydrogen and oxygen. And at 100% thermal efficiency, this reaction requires 39.4 kilowatt hours of energy to produce 1 kilogram of hydrogen. And this process typically requires an electrolyte due to water's low conductivity on its own. Proton exchange membranes, or PEMs, are a type of electrolyzer. They were first developed in the 1960s by General Electric. They use a solid polymer as an electrolyte, and this electrolyte also acts as a gas separator. Here is a basic configuration for a PEM electrolyzer. As seen, there's a cathode and an anode separated by a solid polymer membrane. The water enters in on the anode side. As an electrical current is applied, the water is split as H+ ions diffuse through the solid polymer membrane. They accumulate at the cathode side, where they are reunited with their electrons to form molecular hydrogen. The oxygen from the split water molecule exits out the anode side. So the advantages of PEM electrolysis is that PEM systems typically operate at high current densities. This allows them to have compact designs, high gas purity, and allows them to have quick responses to variable intermittent energy inputs. However, they are disadvantageous because the solid polymer membrane that they use is often acidic, and this requires the use of noble materials for the electrodes. The necessity for noble materials drives up system costs. So the procedure of this thesis is in two parts. First is the system design, and then next is the life cycle cost analysis. The first part of the system design is establishing a use case for the hydrogen. This determines a production baseline, and this production baseline is used to size the electrolysis system. So the use case analyzed in this thesis is decarbonizing transport, which currently accounts for 28% of US greenhouse gas emissions. Fuel cell electric vehicles are one method of decarbonizing transport, as they use hydrogen as fuel. There are currently 18,000 fuel cell electric vehicles in the United States. Assuming each of these electric vehicles consumes, on average, 200 kilograms of hydrogen fuel per year, the resulting hydrogen production baseline is 3,600 metric tons per year. Next is choosing a location. And the two main factors for choosing a location are its wave energy climate and its compatibility with the chosen use case. So the chosen location was off the coast of San Francisco, 50 kilometers directly west of the Golden Gate Bridge, at a water depth of 75 meters. The wave energy climate is high here at about 42 kilowatts per meter crest width. This location was also chosen because California has made great efforts to decarbonize its transport sector through hydrogen fuel cell vehicles. Next was sizing the electrolysis system. So to meet the production baseline, the electrolysis system will consist of 3 plug power EX4250D electrolyzers. The rated input power of one of these units is 10 megawatts, and they have a rated output of 4,250 kilograms of hydrogen per day for a single unit. The footprint for a single unit is approximately 960 square feet, which is equivalent to 4 standard 40-foot containers. And each of these units comes with an integrated support system, such as feed water treatment systems, hydrogen processing, and a power module. Additional support components are needed to support the electrolyzers. Because the overall system draws in seawater, the feed water system of a single electrolyzer is rated for fresh water. Reverse osmosis desalination is required. Additionally, hydrogen has a very low mass density. Therefore, to minimize storage volume requirements, it must be liquefied through a process known as liquefaction. Cryotanks are used to store this liquid hydrogen safely. Here is the overall system is shown here. So first, seawater is taken from the ocean, and then it goes through a reverse osmosis system and is applied to the feed water system as fresh water. This feed water system ultra purifies the fresh water and supplies it to the electrolyzer stack. The electrolyzer stack produces gaseous hydrogen, which goes over to the hydrogen processing system, which dries and purifies the hydrogen before passing it on to the liquefaction system and the cryotanks for storage. Here is the electrical system, which involves the power module of the electrolyzer unit. The power module is used to convert the AC electricity from the wave energy array and turn it into usable DC electricity so that electrolysis can take place. Now, the next step was selecting the hydrogen platform. The chosen platform was a floating production, storage, and offloading vessel, or FPSO. FPSOs are typically used in the offshore oil and gas industry, and their designs typically resemble that of tanker vessels. An FPSO was selected as a platform because of their large deck space to fit the system and all its supporting components, as well as because of their integrated systems such as storage tanks and offloading equipment. So the particulars of the hydrogen FPSO are as follows. It has a length of 200 meters, a beam of 42.7 meters, and a draft of 18 meters. These dimensions were chosen to accommodate the system, all of the system's components on its main deck. A block coefficient of 0.8 was chosen, as this reflects what is typical for tanker vessels. Here is an image of the overall schematic for the hydrogen FPSO. So first, it draws seawater from the ocean. This seawater undergoes reverse osmosis and gets applied to the electrolyzers as fresh water. The electrolyzers produce hydrogen gas, which goes to the liquefaction system, to which afterwards it is stored in below deck liquid hydrogen tanks. After performing an electrical load analysis for all of the hydrogen system components, as well as the hotel and auxiliary loads of the FPSO, the total annual energy demand of this system amounted to 318 gigawatt hours per year. The biggest loads of this system design were the electrolysis plant, followed by the hotel and auxiliary loads of the FPSO. Next was, after performing the load analysis, the wave energy array was designed. The three wave energy converters analyzed in this thesis are the Pelamis P2 surface attenuator, the Wave Dragon overtopping device, and the Aqua Buoy point absorber. These wave energy converters were analyzed to determine their annual energy production at the desired location. After performing this analysis, it was found that the Wave Dragon would be the ideal wave energy converter for this array, as it had a capacity factor of 24%, which is closest to the ideal range of capacity factors, which is between 25% and 30%. The capacity factor of a wave energy converter is the ratio of its average power output at a location compared to its rated power output. And it also had the smallest, it also required the lowest amount of units to meet the energy demands in the array. So the array is shown here. It consists of 23 Wave Dragon overtopping devices, and it measures 910 meters by 4,120 meters with a resulting area of 3.75 square kilometers. Shown on the bottom right is the hydrogen FPSO for scale. All right. So the next part of the procedure is performing the cost analysis. Two particular calculations will be performed in this analysis: a levelized cost of energy, or LCOE, and a levelized cost of hydrogen, or LCOH. So the LCOE was calculated by summing up the net present values of the capital expenses and the operational expenses of the overall system, and dividing it by the lifetime energy production of the system. The LCOH was performed in a similar calculation, except instead of having energy as the denominator, it was hydrogen production as the denominator. So this cost analysis was performed over a lifetime of 25 years with a discount rate of 6%, a corporate tax of 21%, and it used a Macker's depreciation method over a 5-year recovery for equipment such as the FPSO platform itself, the wave energy array, the electrolyzers, and the liquefaction system. This set of assumptions is similar to the set of assumptions that the National Renewable Energy Laboratory, or NREL, uses for their cost analysis of renewable energies. The resulting capital expenses totaled up to 1.45 billion US dollars for this overall system, with the biggest expenses being the wave energy array and the FPSO. The operational expenses amounted up to $23.3 million per year. And here is the LCOE over time. And it has a downward trend over the course of 25 years. So does the LCOH. So the resulting LCOE from these calculations was $179 per megawatt hour of electricity, and $15.89 per kilogram of hydrogen. These numbers were compared to those of other renewable energy sources for the LCOE, and for the LCOH, it was compared to other methods of hydrogen production. So for the LCOE was compared to that of floating offshore wind turbines, and it was found that the wave energy array designed in this thesis is cost competitive with floating offshore wind turbines, as it is 6% less expensive than floating offshore wind. However, the wave energy array designed in this system was found to be 20% more expensive than that of wind turbine powered electrolysis, and approximately 700% more expensive than steam methane reforming, which is a fossil fuel based method of hydrogen production. In conclusion, it was found that the wave energy array, when it consists of wave overtopping devices such as the Wave Dragon, is cost competitive with offshore wind. However, the higher LCOH of this system compared to other hydrogen production systems is primarily due to its system configuration, as the use of an FPSO with onboard liquefaction significantly drives up costs as well as energy demands, which reduces overall system efficiency. Steam methane reforming was found to be significantly cheaper, primarily because it was a fossil fuel based hydrogen production method, and it is primarily a land-based operation. My recommendations for future work would be to examine other use cases for hydrogen, such as for indoor heating as opposed to fueling transportation. I would also recommend analyzing different types of wave energy converters, such as the oscillating water column developed by this year's MEC team. I'd also recommend examining different system configurations that used less expensive platforms other than FPSOs, and different storage methods, such as leaving hydrogen in its compressed gas state instead of its liquid state. Thank you all for listening to my presentation, and I would like to ask you to please save all questions for after Ashley's presentation.